Alright, today I have for you a vector addition problem. We're going to handle this one both graphically and mathematically, and it will be a good counterpoint to the example we do in class on Monday, and good preparation for both the next workshop and for your first midterm. So, this problem starts off with you going hiking in the woods. First you travel 2 miles due south, then you travel 3 miles in a direction 38 degrees west of south, then you travel 2.5 miles in a direction 50 degrees north of west. And we want to know, at the end of your hike, how far and in what direction are you from your starting point. So this is going to be a vector addition problem. And we have 3 steps here. First, we travel 2 miles due south. I'm going to call that vector A. Then we travel 3 miles in a direction 38 degrees west of south. I'm going to call that vector B. And last but not least, we travel 2.5 miles in a direction 50 degrees north of west, and I'm going to call that vector C. Now what this problem here is actually asking for is asking us to add up these 3 vectors to get our total vector R. Now each of these are displacement vectors, so just like we did in one dimension when we were finding the total displacement for the average velocity, if we add up our individual displacements, we get the total that we will call the resultant vector. The resultant vector is what you get once you finish adding up other vectors or subtracting other vectors. It is the result of all of that addition or subtraction. So first, it'll be good to do this graphically, just to get an idea what this might actually look like and what types of numbers we would expect for our final answer. So I've talked about this in class already, at least briefly, but to do a graphical vector addition problem, you have to pick a starting point, and then you connect all of your vectors tip to tail, starting from that starting point. So first is vector A. And vector A involves going 2.0 miles straight south. And then the next step is vector B. So now from the tip of vector A, we attach the tail of vector B. And vector B is 3.0 miles in a direction 38 degrees west of south. Whenever I give you a direction like this, west of south, it's the second one that is the reference line. So here is our reference line there. So from south, this angle is measured 38 degrees to the west from there. And in case you need a little reminder about what the compass rose looks like, here it is up here at the top. Then we continue our tip to tail adding here, except this time we're starting at the tip of vector B, and now we're going to add vector C from there, which is in a direction 50 degrees north of west. So in this northwest direction, vectors might not be perfectly to scale, but this is vector C, and it has a magnitude of 2.5 miles. So north of west means west is our reference line, and our angle is measured north from there. So here is where that 50 degrees goes. So once we've gotten to this point, we need to find our resultant vector. And just like we labeled our starting point, we can label our ending point over here. And then for our resultant vector, our resultant is the vector that connects our starting point directly to our ending point. So from the graphical way of doing things here, we can see that our vector r points southwest. So when we do this thing mathematically, we'll need a coordinate system. Let's just pick that right now. X positive to the right and y positive up. So since this vector points down and left, that means we know what to expect about our components of that vector. We should expect the x component of the resultant vector to be to the left or negative with our coordinate system. And we expect the y component of the resultant vector r to be in the southward direction or also in the negative direction. Now here we have a pretty clear direction for r, but we might end up with a problem where it's not quite so clear, where y might be positive or might be negative. It's kind of difficult to tell exactly without getting out the ruler and drawing each of these vectors to scale and using a protractor. But it at least gives us some helpful things to expect later on. To do this mathematically, we need to take our coordinate system and split our vectors into components. Because now that we have both the x and the y direction going on, it's not as simple as just adding and subtracting 2 and 3.0 and 2.5 until we get our answer. So we have to split vectors a, b, and c into their x and y components. I'm going to switch to the colors for this one. So for vector A, this one's pretty straightforward. Vector A points due south. That means all of vector A is in the y direction and none of it is in the x direction. So AX is 0 and AY is the whole magnitude, that 2.0 miles. And in the southward direction, which is our negative y direction, so we have to put a negative sign there. We can do the same thing for vectors b and c as well, where that little arrow over the top means that it's a vector. So bx is going to be the x component of this vector b over here, and you guys can work through, if you need to, the trigonometry step by step. But here's the triangle made by vector b, and the x component of vector b is going to be the opposite component of that triangle. So what we'll need to do is take that 3 miles and multiply it, since it's the opposite, by the sine of our angle, 38 degrees. And we also need to check for direction. Bx points to the left. Remember, the components of a vector are also vectors themselves. So the left is the negative x direction. And when we plug this in, we get a value of negative 1.85 miles. By is a similar story. We still have the magnitude. And since we have the hypotenuse and we're looking for the adjacent side now, we need the cosine of 38 degrees. And again, we should check our positive and negatives here. By points down, south, which is the negative y direction, so we do need a negative sign there. And this gives us an answer of 2.36 miles in the negative direction. Lastly, we do the same thing for vector c, where cx is going to be, again, our magnitude, 2.5 miles, times now the x component of this vector right here. Kind of try to draw out the triangle for you. Part of it's hidden under those labels. But the x component is now the adjacent component, which means here the x component is going to be cosine rather than sine like it was before. X won't always be cosine, but cosine will always be adjacent. So adjacent here is the x component. Adjacent for vector b was the y component. We also need to check our positives and negatives again. The x component of vector c points to the left, so that's negative, so we need to toss a negative sign on here, and we get that the x component of vector c is negative 1.61 miles. cy, the last component here, again, we're going to take the magnitude, and we're going to multiply it this time by the sine of 50, because now we need the opposite component. And cy points north, or positive. So no negative sign necessary here. We get positive 1.92 miles. Once we have all of the components of each of our vectors, we can combine them. Because this equation up here at the top, the vectors we're adding, we can't just add the numbers, but we can add the x components and the y components separately. So you can't just add 2, 3, and 2.5, but ax plus bx plus cx does equal rx. And the same thing for the y direction. The the y component of vector A plus the y component of vector B plus the y component of vector C will give you the y component of the resultant vector. So we have a helpful way we can keep track of this with a little table where we make our x and our y directions on that table. And we want to add up vectors A, B, and C. And once you add all of those together, that gives us our resultant vector R. So now we just need to fill in this table. Vector A had an x component of 0 and a y component of negative 2.0 miles. Oops. Vector B had an x component of negative 1.85 miles and a y component of negative 2.36 miles. And vector C had an x component of negative 1.61 miles and a y component of positive 1.92 miles. Now we can add each of those columns up separately. For the x column, we get negative 3.46 miles. And for the y component of our resultant vector R, we get negative 2.44 miles. Now we have what we need to find our resultant vector. Remember, there are 4 things you can know about any vector: the x component, the y component, the magnitude, and the direction. And once you know any 2 of those things, you can find the rest of them using trigonometry and Pythagorean theorem. We now have Rx, the x component of our resultant vector, and Ry. So we know 2 things about this vector, and now we need to find the magnitude and the direction. So it can be helpful to draw out our vector. So here is Rx, and this side has a length of 3.46 miles. You'll notice I left the negative sign off here because I drew Rx to the left. So I've already accounted for the negative number by the direction that I drew it. And the same thing for Ry. It's negative 2.44 miles, but I'm just going to put 2.44 miles. And I've already accounted for the direction based on drawing the x component downward. Sorry, the y component directed downward. And these add together to give us our total resultant vector R. So you'll notice that A plus B plus C equals R, but for any vector really, the x component of that vector plus the y component of that vector equals the vector itself. So to find the magnitude of r, just r without the little vector sign, we want to take the square root of rx squared plus ry squared. That's just the Pythagorean theorem. And once we plug in those numbers, so just so you can see what's going on here, the square root of negative 3.46 miles squared plus negative 2.44 miles squared, we get a magnitude of 4.23 miles. So this is the magnitude. This is how far we are from our starting location. Then to figure out in what direction we are from our starting location, go back to this triangle that you drew earlier, and label an angle in it, preferably one by the tail of the vector. So here's our tail of the vector. I've labeled that theta down there. Now some quick trigonometry can tell us, well, we know opposite and adjacent, so we're going to need tangent, and skipping a step or two in the math, the inverse tangent of opposite, 2.44 miles, divided by adjacent, 3.46 miles, will give us our angle theta, which for this problem turns out to be 35.2 degrees. But all angles need a reference, just like the west of south from above. So this angle is measured between this line and the actual vector itself. Well, this line, the x component there, points west. And then we measure our angle south from there. So we say that this is 35.2 degrees south of west. Or, if you prefer, let's double check this. You could also do 54.8 degrees west of south, which turns out to be the same thing. Either one of those would work. Or you can do things like clockwise from positive x or counterclockwise from the negative x direction. Any of those. In class, we'll do an example where the resultant is not the unknown, basically where we know vectors A, B, and R, but we don't know what C is, so that's a slightly different example, but it's still the same basic approach. We're still going to draw our vectors to make sure we know which direction they point, split our vectors into our x and y components so that we can put them in this table down here, which is written based on our vector equation. So hopefully you can see this equation up here, right there. A plus B plus C equals R. And once we do that, we add up our x and y separately to find our x and y components of our resultant vector, or of the vector we're trying to find. Use Pythagorean theorem to find the magnitude, and then do a little bit of trigonometry to find the direction, making sure we include a reference. So there will definitely be a problem like this on your midterm. It will also be the topic of workshop on Tuesday of this week. So do make sure that you get a chance to look over this video and practice this kind of stuff. We'll do another example in class and then another example in workshop. That should be it for today. Thanks for watching, and I will see you in class this week.